So thank you again for being here, John. And John will be presenting on Introduction to Tezos. So go ahead whenever you're ready.
Cool, thanks everyone for joining. So the title of this talk is Introduction to Tezos and Tools for Building a Tezos Dapp. And it's really a quick rattle through all of the things that I've discovered in the last year or so of developing on Tezos to try to get everyone up to speed as quickly as possible. Everything I mention in this talk is available in our GitHub, which I am posting the link to the chat now. So if you want to check the source code out for stuff that we talk about, just look there. So quickly, just an introduction to Tezos in facts and figures. Tezos is a second or third generation blockchain. It currently has a 60-second block time, but this will be 30 seconds in the next release and 10 seconds by the end of the year. We support 3 elliptic curves, called TZ1, TZ2, and TZ3, which gives a lot of compatibility with third-party key signers and services which provide key management. The official implementation of Tezos is called Octez and is written in OCaml. There's also a Rust node which is in development. Tezos is a proof-of-stake blockchain, and miners in Tezos are referred to as bakers, which I think is a reference to the French background of Tezos. We have on-chain democracy, and because of this, the chain is auto-upgradable. So typically every 3 months, there's a new version of the protocol, which addresses smart contract features, gas cost, privacy, zero knowledge. Every time there's a release, there's new features, and typically contract execution gets cheaper. Smart contracts use a stack-based VM, which we'll be coming to in a bit, and inter-contract calling has a different model than Ethereum. You are subject to a maximum gas per contract call, but you don't pay extra for how much gas you use as long as you remain below that minimum. And the native Tezos token is called Tez. Today, we're going to talk about a few components. We'll talk about the node a little bit. We'll talk about 2 smart contract languages, 2 of the most popular ones that people are using right now. We'll talk about a JavaScript library written in TypeScript called Taquito and a Python library called PiTZOS. So our node is relatively easy to run oneself. I know that the Ethereum node now requires quite extraordinary hardware requirements. Ours are pretty low. I've run nodes off of Raspberry Pis on the testnets at least. As I said, there's a new version every 3 months, and there's a Dockerized sandbox version called FlexTeaser for testing. There's a link to that in the GitHub repo, which I sent earlier. There are a variety of public nodes. Again, there's a list in the repository, and there are multiple testnets. Usually we run 1 for each version, and we run a few historical ones, which tend to become disused relatively quickly. The node comes with the Tezos client command line tool, which is useful for contract interactions. And again, we'll be seeing a few of them later. So I don't know how much all of you know about smart contracts. So this may not be new to some of you, but I just wanted to go through some of the characteristics of smart contract programming. Because of the limit on gas usage by a contract, all operations inside a contract must be O1. So typically you can't loop unless you know that you're going to loop 2 or 3 times and that's it. You can't recurse. You should aim to do everything on an ongoing basis on every contract call rather than having some big bang calculation at some point in the future. When the contract is invoked, and every time it's invoked, the storage is loaded and parsed, and this uses gas, except for a data structure, which is called a big map, which is loaded on demand and is cheaper. But you cannot iterate through the keys in the big map, and they can only live at the top level in the contract storage. Inter-contract calls in Tezos happen after the calling contract is done, and storage is expensive. So just following on from the earlier point, data storage on the blockchain is extremely expensive. It's 0.001 Tez per byte, which sounds like not very much, but which works out in practice to $2,000 per megabyte. Sometimes it's illegal to store data on the chain. If you hash sensitive data without a salt, that can be sensitive. Ciphertext of sensitive data is sensitive. So typically we don't do that. We store a hash of the data on the chain and we put the data somewhere else. So as a general rule, the blockchain just records ownership and does not store the thing which is stored. This is a digression from the main point of the talk, because I don't think any of you will actually be writing Michelson, but the thing that you see on the right-hand side of the screen right now is the native assembly language of the Tezos blockchain virtual machine. And as you can see, because it's a stack-based machine, it has an awful lot of stack operations, these drops and digs and drops and swaps. It's not very human friendly, but because it's extremely simple, it supports formal proofs. So if you want to prove your contract correct and you're in the position to write a mathematical description of it, you are in luck. In Tezos, contracts are pure functions. They are called with a parameter and storage, and they return a list of operations to be performed and the new updated storage. So in this presentation, we're going to talk about a sample problem, which is one that we are actually solving for someone at the moment, which is a very simple voting application on the blockchain. The rules are this. There are three kinds of people. There is one administrator who can create polls and add and remove eligible voters. Eligible voters are in this list and may vote in polls. If they vote multiple times, only their last vote stands. The contract will keep a running total of the votes in each poll. Each poll has a number of valid questions and an end date after which no votes will be counted. And people can vote as often as they like, but only their last vote is counted. So for this, we sketched out what you might imagine to be a good storage if you are a programmer used to programming in a normal language. So this is written in Camaligo, one of the languages we'll talk about today. It's an ML-based language, but I think it's relatively understandable. And as you can see, what we do is we build up types, and then at the end, our storage is essentially a set of maps of addresses against votes or totals, and all of this. If we deploy this on the chain and we are successful, because this data must be loaded every time the contract is loaded, as the contract is used more and more, every load will incur more and more weight, which is absolutely what we don't want to intend. Contract fees are paid by the caller, so everybody who votes is going to pay a little bit more as the contract builds up data and that data is built and parsed. And so we end up with this slightly convoluted structure in which we use this big map type, which is only loaded when it is required to be loaded. So each element in the map is only loaded when it's called for. And so, of course, what we have to do is always index everything by all of the things that make up the key. So address and poll ID makes up the votes. Totals are voters are an address and a unit. So an address and an indicator of whether they're present or not. So you can just put the address in. If you get something back, they're a voter. If not, they are not. And this is a good structure for a smart contract in Tezos, because as we scale the contract up, as more people use it, the gas cost for the callers will not increase. So the first language I'm going to talk about in this whirlwind tour of Tezos is Camaligo. It's one of the Lego family of languages in Tezos. There are 4 syntaxes at the moment. One resembles JavaScript, one ReasonML, and another one Pascal. The syntax of Camaligo is that of ML, one of the first functional languages. Camaligo is the most mature of the Lego languages and looks like OCaml, which is the native language of the node. It's a bit of a steep learning curve for many people, but we find it the most natural way to code for Tezos, but we want to emphasize that it's up to you. The other most popular choice is SmartPi. I think at this stage, everybody on the planet knows Python. SmartPi is a metaprogramming language. So when the script is executed, Michelson code is emitted, and when the Michelson code is run on the browser, it's run there. So you write a program which generates a program which is then run. Because Michelson is extremely strongly typed and Pascal and Python is extremely weakly typed, you really have to give some big hints to the Pascal interpreter, to the Python interpreter, sorry, about what's going on in your program. The optimization in SmartPi is not nearly as good as Camaligo, although opinions differ. And it has its own built-in Michelson VM, which means that you can write unit tests inside your SmartPi program, which is not so easy in Lego. Both of them are great choices for writing smart contracts on the Tezos blockchain, and we can't recommend one over the other, really. So this is an example of a SmartPi program. It starts with the import, and then it defines a class which inherits from the contract. The init method initializes the contract and its storage, and the methods that you see afterwards are smart contract methods, which are called the one at the bottom, which is labeled, oh, sorry. Today, the one called create poll internal, you can see that we have to give type hints in here. So we say tot equals sp map, t key equals sp.tnat, value equals sp.tnat. This is necessary because the code that will be emitted has got types in it, and of course, the Python doesn't really know about that. This is not from our example. This is from the docs, for which I apologize. And it's just to show how you originate a contract using SmartPi. So contracts originated on Tezos are uploaded with code and with an initial storage, which is typically the configuration that you want the contract to run with on its first invocation. And SmartPi handles these details for you. So you point it at the code, you point at the storage, and it generates all of this stuff. In this sense, SmartPi does a better job, I think, of handholding for developers who are not so super familiar with Tezos. So as I said, when we deploy a contract, we do several things. We upload it to the chain. We may transfer Tez to it. We almost certainly initialize the storage to something appropriate. And what we get back from that is an identifier, which starts with KT1. At the time that we initialize a contract, we pay for the storage used by the contract. So the larger the contract, the more storage you're going to have to pay for. So this is an example of compiling using Camaligo. So we point Lego at the contract, at the source code, and at the entry point, and it kicks out some Michelson code for us, which looks like this. We can then also compile our storage with Lego, and this produces, so we put in some empty big maps and the address of an administrator, and what we get out is this extremely terse bit of data which defines the initial storage for the contract. So I just wanted to show this to show how we originate the contract on the blockchain. We use the Tezos client, which comes with the node, and we tell it to originate a contract. We give it the name poll, and we optionally transfer Tez to it. In this case, we transfer 0. We say that it's running the TZ code, which is Michelson, and we init it with the value that we got back from compile storage earlier. Because we're operating on the testnet, we get warned that we're not on the mainnet, and then we get a fatal error. Because we haven't told the command line that we're happy to burn stuff for storage, it refuses to do so, but it tells us how much short we are. So then we try again, but we do it again with the -- burn cap argument at the end. And we get told the estimated gas is this, the estimated storage is this, it's been successfully injected. And then the Tezos client waits for the node to include the operation. And it comes back at the end with a contract address, which you see under originated contracts, and balance updates to say that my account has paid for all of this. So Taquito is a TypeScript library which makes it relatively easy to interact with contract on the node. This is an excerpt of some of the code which you will find in the GitHub repo, which accompanies this presentation. We built a whole application there so that any of you can just look at what we did to make this relatively simple thing and hopefully use it as a springboard to your own Tezos applications. As you can see at the start, we initialize the contract. And so we put the address in and we wait for the wallet, the adapter, to connect to it. And then we have this create poll method, which calls a method in the contract and returns the hash of the operation that was called. In order to connect to your wallet to Taquito, we recommend using a software library called Beacon, which is a Tezos standard for connecting wallets. There are several wallets available for Tezos. There's Kukai, Temple, Galleon, and several more. By using Beacon, you can use direct auth, which gives your users the opportunity to sign transactions using their Google or Facebook login or any SSO. And the sample code in the repo, again, tells you all of this. Our strong recommendation is to use Beacon. And lastly, in our really quick tour of all of the SDKs, there is PiTZOS, which is not only very good for any time you want to write a server-side Python script, but it's also extremely useful as a REPL for testing your contract when it's deployed. So what you can see in this little code snippet is that I initialize the PiTZOS client using a private key in plain text. I point it at a node, which I'm running myself. I point it at a contract. And at this point, the contract object automatically generates methods to access any of the contract's entry points. So you can't see it here, but if I just type contract dot and hit tab, it will tell me all of the entry points that it knows about. If I type contract dot create poll and don't give it the correct arguments, it will tell me the structure I need to invoke the method on the contract. So it's super, super, super easy when you deploy a contract to check that it works by just pointing PiTZOS at it and asking PiTZOS what the contract can do. Of course, Tezos has a number of indexes. It has indexes because the node is slow, and its most glaring fault in daily use is that it cannot tell us all of the keys to big maps, which typically are things that are very important to us. So we need something that can cache the data for us, and there are several indexes for Tezos. The ones that we in our team use most often are Better Call Dev and TZKT. Using these, you can inspect your contract, you can look at its storage, you can see operations that failed. It's super useful. And all the indexes are open source and can be run on your own machine using Docker. This is just a screenshot from TZKT for the polling contract that we've been talking about. And this is the storage view after running the operation showed in the PiTZOS example.
Thanks again, John. If anyone has any questions, feel free to raise their hand or drop questions in the chat.
Yeah, I have a quick question. So could you kind of elaborate a bit more on, I guess, how easy it is to learn coding with Michelson and the other flavors that you just mentioned in comparison to, say, Solidity, for instance?
Yeah, so I mean, I think Solidity has more of a easy environment for people who are used to imperative programming because it just treats the contract as a big lump of data, whereas we have this very functional way in which methods are pass parameters and get parameters back. So there's a certain amount of paradigm shifting necessary to think of everything as an input and an output. But when you do get used to that, I think it's much easier on Tezos because it's very clear what's going on at every stage. So it really encourages one to write clear programs and also to write stuff that's easily testable.
Thank you.
Cool. I have a couple here. So would you say data modeling is the hardest part of SC Dev? Yeah, I mean, I think it's probably the most difficult part of all development, to be honest. But yeah, definitely when you come to it for the first time, having been used to having like megabytes of memory and thousands of clock cycles to just burn all the time, getting used to building things up in a way that the cost of operations is amortized over operations rather than being paid for all at once. One naturally has this tendency to think, oh, I'll just run a batch operation once a day and that'll sort everything out. But you cannot do that in a smart contract. So you must think, right, how can I update this total on every invocation of the contract in a way which means that the data is always up to date and everybody pays the same amount for this update. Cool. And another question, any examples or resources for implementing FA 1.2 or FA 2 tokens on Taquito? So the tokens themselves are implemented in the smart contract languages. So in SmartPi or in Camaligo or in whichever else. In terms of things which permit you to access those things, yeah, there absolutely are. Let's see. Yeah, so for example, let me just put this one in. Here's a good article. So this is one from the TQ Tezos, which tells you how to access an FA 1.2 token using Ligo and Taquito. And generally, if you just search on the web, there's a lot of resources for Tezos.
Sounds good. And then we have one other question from the Discord. I have started working on an MVP. I just wanted to ask if it is necessary to provide a white paper if they are already building a prototype.
Yeah, I mean, this is more of a hackathon question, but yeah, I guess this is a good thing to tell everyone. Absolutely. The reason that we said that white papers were acceptable was that if somebody has a great idea which they made an amazing white paper from, of course we're going to accept that as a potential winner of the hackathon. But in general, if you have an MVP, then that's wonderful.
Any last questions? Sounds good. Okay.
Oh, actually, I have one more. I have one more question. Could you further elaborate on the implications of Granada, the latest upgrade that's going to happen on the Tezos chain, and how that'll affect everything moving forward?
Yeah, I think the most noticeable thing is going to be that it's going to halve the block time so that things are just going to go through more quickly. I think as with every other upgrade, it's going to have reductions in gas cost and increases in storage. This is kind of one step on the way to Tendermint, which is Tezos implementation of Tendermint, which is the fast finality system. So this is going to cause Tezos to absolutely rattle through transactions really very quickly, and also that one will be able to be sure that one's transaction is on the chain much more quickly than now, when one should wait several blocks.
Well, I guess with that being said, how do you think this will help, I guess, propel Tezos' emerging DeFi space? I mean, we're seeing plenty DeFi emerging. We're seeing Crunchy Network coming out. We're seeing Salsa DAO. We're seeing all these DAOs and these protocols starting to really emerge and fit in their own niche, if you will. So what's your take on that?
I mean, my hope is that it's going to accelerate the adoption of Tezos. At the moment, we are seeing a lot of NFTs coming to us, and yeah, lots of people being attracted to Tezos. So my hope is that that's going to continue and accelerate.
Thank you.
And then the last question from the chat is
best place.
Yep, go ahead. You got it.
Yeah, I mean, Discord, I'm very new to Discord because I'm old and I catch up to things very slowly. I am JS Newbie on Discord. I'm JS Newbie on Telegram. And I'm JS Newbie on Twitter. So anybody who wants to get in touch with me can just reach out on any of those channels.
Perfect. Thanks again, John, for coming in today. And thank you everybody for coming out to this session. And this recording will be available on YouTube and also in the Discord. So thank you.
Thanks very much.
Have a great day, everybody.